Thank you very much. Thank you also to the organizer for this beautiful and exciting conference. And so I will speak about smooth decomposition for driven-dissipative multimode boson interactions. So first of all, I would like to thank all this collaboration that originated these results. In particular, Elie Gouzian, who was a PhD student in 2020 in Nice University, Virginia Dauria, and after Bacao continued the work started by Elie. So consider your favorite more than quadratic Hamiltonian in the field operators. Apply your mean field approximation. You consider small fluctuation around this mean field theory, and you get an effective quadratic Hamiltonian that consists in two different kind of terms. The first kind, the GMN, destroy an excitation in the mode N and create an excitation in the mode M. So you know that this term has mode hopping, and the F terms produce pairs in a couple of modes M and N, or destroy them. So, and then you collect your field operators in the column vector xi, and so you can parameterize your Hamiltonian to a matrix H calligraphic, which contains all these terms in the most general way. And then, for example, if you want to follow the evolution generated by the Hamiltonian, for example, in Heisenberg picture, you find, because the Hamiltonian is quadratic, a linear evolution, so a set of coupled differential equation which are coupled to this matrix. And now the question is, how do we solve this coupled system of equations? So you might think, okay, we can try to diagonalize, but the problem is that diagonalization does not lead to new linear combination of the boson modes that still preserve commutators. So you don't find new physical observables. So we say that the transformation is not symplectic. And then, of course, you have another strategy, which is to follow to adopt the Bogoliubov-Valatin transformation, but actually this is not always possible. It is only possible if this H matrix is positive, and in a driven system this is not the case. And then if it is true, however, then this coupling matrix can be decomposed in this way, where lambda is the diagonal, so NB is the Bogoliubov transformation, which is a symplectic transformation. This means that preserve the commutator algebra, but it is not unitary in the sense that it can contain also amplification, the amplification processes. But nevertheless, you can define new modes, Bogoliubov modes, and then your Hamiltonian is completely decoupled and trivial. Yeah, and so in the same way, also your system of coupled equation. But from the point of view of someone that works in quantum optics, still there is a problem. The problem is that even if you can use this decomposition, how you can quantify entanglement or squeezing or quantum correlation associated to the dynamics of the small fluctuations, and in the laboratory, how do you measure them? So these correlations are hidden in the definition of the modes, of the Bogoliubov modes. So what a quantum optics or quantum optician would like to do is to have a symplectic unitary diagonalization. So where U not only is unitary but also symplectic. Okay? But there is a theorem that states that this is not possible unless either G or F are equal to 0. But so this means that this constraint make more trivial the set of problems that we can study. So the change, a different approach would be first to write the formal solution of your system in terms of the exponential of the Hamiltonian. This exponential connects the input at t equal to 0 to some output, some time, finite time t. And in this case, this matrix is always possible to symplectic decompose in this way. This is known as block-Messier decomposition. Okay, and typically, since the vacuum modes are unitary invariant, in general, if your input is vacuum, the matrix V does not play any role, while the matrix U defines the normal modes of your problem, which is completely decoupled, and D contains the amplification, single mode amplification or deamplification processes. So in general, your quadratic multimode interaction can be split in 3 steps. The first one is a multiport interferometer, so this is the physical interpretation of these unitary symplectic matrices, and the diagonal part are single mode squeezer. Okay, so this is the perspective, and now our work was to generalize this perspective to driven-dissipative problems. So again, you can start from your favorite more than quadratic Hamiltonian, derive in Heisenberg picture nonlinear quantum Langevin equations, then take the classical limit, the mean value of this, and you find the equation describing the evolution of your mean field. So this will, in the mode representation, will give you coupled mode theory. In the total field, this could be very often correspond to Lujato-Lefebvre equation, or in condensed matter community, driven-dissipative Gross-Pitayevsky equations. And then you take your field operators and you linearize with small quantum fluctuation around the mean field in order to get the linear quantum Langevin equations. So, okay, here I collect again the real part and the imaginary part of the complex field amplitudes in the R column vector, and your linear quantum Langevin equation looks like this compact set of coupled equations. So here you have the dissipation, here you have the input fluctuations, and in the matrix M you have encoded again the couplings corresponding to an effective quadratic Hamiltonian of your Bogoliubov theory. And again, so now the idea before to decouple the system is to solve formally the dynamics. So since the system is linear, so it can be solved in terms of transfer function S of omega, which you can understand also as a Fourier transform of the green function of your problem. And this linear, this transformation connects the input fluctuation to the output fluctuations. And actually, the only thing you have to check is that this S of omega has the good properties, such that the R out quadrature are the Fourier transform of bona fide quadrature operators. So this transfer function, which is a smooth function of omega with matrix values, must be, we call this omega symplectic, which means it must be continuous, smooth on omega, and for each value of omega, the 2n by 2n complex matrix must be conjugate symplectic. Okay, this is the property for S that S needs to satisfy, such that a route corresponds to Ft of bona fide quadrature operators. And now you try to decouple the system. So the goal is to find linear combination of modes such that they decouple the problem, so they are normal, define physical observables, so preserve the symplectic structure of your problem, but also treat smoothly the time and frequency. And so we proved that such decomposition exists that preserve the smoothness. So this means that you can take your S of omega, decompose in this way, but now you don't have matrices, but you have transfer functions, and but you still can prove that U, D, and V can be smooth with respect to omega. And so actually U and V are smooth unitary and omega symplectic transformations, and D of omega is a smooth diagonal matrix that encodes the quantum fluctuation in single mode squeezed, frequency dependent squeezed state. And since U of omega give you the coefficient of the new linear combination, but these coefficients depend on the frequency, and typically you don't have the same linear combination for the same frequency, so you have this frequency dependence, because on this idea we called these supermodes, morphing supermodes. And physically this object, as the U, the matrix U unitary can be interpreted like as an interferometer, this U matrix can be interpreted as an interferometer based on a cavity. So the cavity brings the idea of recirculating some information, so some memory, and so we call this interferometer with memory effect. So just pay attention that if you apply Bloch-Messier decomposition point by point in omega, you may not find satisfy the point number 3, so you don't preserve the smoothness. And this idea of morphing supermode, even if in the context of highly multimode system is somehow new, well, it was very well known in single mode quantum optics because it is simply frequency dependent squeezing, and this is was very well known in single mode OPO, ponderomotive squeezing, broadband squeezing. Also, all these systems already present this frequency dependent character of squeezing, and recently some new works rediscovered a little bit this frequency dependence of the squeezing, in particular in improving the sensitivity of gravitational interferometers. They engineer the frequency dependence of squeezing in order to have reduced noise, reduce intensity noise in high frequencies, and reduce phase noise in the low frequencies of the interferometer. Okay, and then you apply this machinery to your favorite your favorite problem. So I won't go in the details of this particular problem, but this is very general. You can apply to any other kind of problem. So, but if you apply this machinery, so this you find the classical solution, so the mean field steady state solution, and then you apply your machinery, and you get the spectral squeezing or frequency dependent squeezing, and for example the structure of the most squeezed morphing supermode. So you see that on the longitudinal horizontal axis you have the frequency dependence, in the vertical axis you have the coefficient of the 101 longitudinal modes of your cavity, and for a particular specific frequency omega, well, you get a supermode, a linear combination, which is given by these coefficients. So it is very important that these supermodes are complex. I will come back to this in a few slides. But now, okay, can we measure these supermodes? So in quantum optics, the typical device for measuring quadrature squeezing is to use local oscillator detection, which consists in taking the output of your source of quantum correlations and send it through a 50-50 beam splitter, making it interfere with a strong coherent field, which is the local oscillator, detect the two photocurrents here, subtract them, evaluate the variance of the photocurrent, and make the Fourier transform of that. And so the strong local oscillator, because we are in presence of multimode field, must be also multimode. So the alpha m encode the coefficient of each each frequency constituting the local oscillator, and also we can store them in a column vector in this way. So the x are the real part of this, the y are the imaginary part of alpha. And then if you calculate the photocurrent, you realize that actually the projective nature of this measurement, it is expressed by this scalar product between the column vector of the local oscillator and the column vector of the modes that are measured by the homodyne detection. And if you measure the noise spectral power, this will be given by the covariance matrix of your system. We are in the Bogoliubov of approximation, so our state is approximated by a Gaussian state, so it is completely described by covariance matrix, and it is sandwiched between this local oscillator vector. Okay, and now you discover that, for example, if you try to measure the squeezing of the most squeezed supermode, so this is this solid blue line, no matter the Q, so you can optimize at best your Q, you will get this gray curve. So there is a discrepancy between the total amount of quantum correlation generated by your system and the amount of squeezing that you can detect. Okay, and actually this discrepancy, we dubbed it as hidden squeezing. Actually, the first work on hidden squeezing was done in 2013 in a single mode configuration by the group of Nussensweig in Brazil, and then it was independently developed later in optomechanical context by the group of Stamper-Kern, and they call it complex squeezing because the covariance matrix, actually the spectral covariance matrix, is complex and not real. And so also this group proposed different strategies in order to detect the optimal squeezing that is generated by the system. So our method actually is more general and is particularly adapted to the multimode context. So the idea is the following one. So you see that the problem of this discrepancy is the fact that your morphing supermode are frequency-dependent functions which are complex, while your Q vector is real and frequency-independent. So you can never mode match this in order to detect optimally the degree of squeezing encoded in your supermode, because the scalar product will be never equal to 1. So the idea is to introduce some interface between the homodyne detection and the source in order to produce an effective generalized local oscillator. So and this is just a matter of linear system, because you know that if you put here linear system with transfer function SEME of omega, so the covariance matrix at the output here will be sandwiched between these transfer function, and then when you evaluate the spectrum of squeezing, this will come up with a generalized local oscillator, which is given by the standard homodyne local oscillator multiplied by the transfer function of your interface. So if you design your interface such that this generalized local oscillator match exactly your morphing supermode, then you have the possibility to detect entirely the optimal degrees of squeezing generated by your source. And so, well, okay, this is just the fact that this transfer function does not have to introduce more correlations, so it must induce a unitary transformation. So this means that the quadratic Hamiltonian associated to this system must contain only terms of this kind and not terms of squeezing, of pair production. Okay, so if so we found a way to experimentally implement this this interferometer, so this transfer function, so this interferometer with memory effect. In the case of 4 modes, for example, so here you have a scheme of the interferometric scheme, and this point here are where the mode number 2, for example, and the mode number 3 interfere in this object, which it is actually a frequency beam splitter in the case your modes are different frequencies. So I won't detail much about the physical details of this frequency beam splitter, but they exist. They have been proposed by Marco Loncar's group, and they can be used in order to implement physically an interferometer with memory effect. And so this is the object that you can put between your source and your homodyne detection scheme in order to mode match the quantum state to the local oscillator of standard homodyne detection. Okay, this is a single mode implementation, but the philosophy is the same. And so, for example, now you take your source of multimode quantum state, so for mode, for example, and you try to measure the squeezing through a standard standard homodyne detection. For example, you want to measure the best optimal level of squeezing, which is this solid red curve, and no matter the local oscillator, you will never be able to touch at any frequency but the first one, omega 0, you will never be able to detect the full degree of squeezing carried by the output state. But then you use your interferometer with memory effect in order to mode match the source to the detection scheme, and then you can see that you can optimally recover the full squeezing spectrum. Okay. So this means that you are actually, this object is actually projecting on the supermode. So the supermode has actually the structure of this physical object. And so, okay, this is my last slide. So one of the last results we got is that actually we discovered a phenomenon of avoided crossing, degeneracy, and Berry phase in the spectrum of squeezing. So this is something which is not connected to the avoidance of crossing that you typically found in the spectrum of the Hamiltonian. So this is not a feature carried by the Hamiltonian. It's a feature generated by the dynamics and the noise, the quantum noise of the system. And so you can see that the squeezing spectra at certain frequency, they avoid to cross, okay? But if you tune the parameters, the experimental parameters of your system, you can find a point, the optimal spot where you have a true degeneracy of the squeezing spectra, and actually if you draw a sphere around it and you trace path along the parallel of this sphere, and you count you trace the phase accumulated by the eigenvectors of your problem, you will see that this eigenvector in correspondence of if you turn around, if the sphere is centered around this degeneracy point, they will accumulate a multiple phase of 2 pi. Okay, and this comes with the topological charge +1 for the supermode, the green one, which is the number 3, and the topological charge -1 for the supermode number 2. Okay, so but this we have not really explored deeply this effect, and so this is the conclusion of my talk. So I proposed you a general method for the complete characterization of quantum fluctuation in time and frequency, at least in the Bogoliubov approach. So we found complex morphing supermodes which introduce a problem of mode matching for standard homodynamic detection that we can solve by using interferometers with memory effect. This can be used as a tool for tailoring the generation of multimode Gaussian quantum state, for example, in frequency combs, but in general in any driven-dissipative system that you like. And for future perspective, for example, it would be nice to extend the study of the quantum properties to the light generated by inactive devices like quantum cascade laser or interband cascade lasers, and eventually investigate the relationship between topological properties in the Hamiltonian, how they reflect in the dynamical properties of the system. Thank you very much for your attention.